Yeah, done. So hello everybody and welcome to another session of the IFIMAC plus ICMM joint seminar series. My name is Elsa Prada and I will be chairing this talk. As usual, the session is being recorded and will be made available later on YouTube. You can ask questions during the talk and also at the end of the talk by raising your hand or writing them in the chat. If you do it during the talk, please write them, and then at the end we will unmute the microphones and you will be able to talk. So today it is my pleasure to introduce our next speaker in this series, Lars Fritz. Lars is an associate professor at the Institute for Theoretical Physics in Utrecht University, the Netherlands. He did his PhD at the Institute of Theoretical Condensed Matter Physics in the Karlsruhe Institute of Technology in Germany back in 2003-2006. And then in 2007, he moved for a postdoc to Harvard University in the USA, to the Department of Physics. And then in 2009, he became an Emmy Noether research group leader in the Institute for Theoretical Physics in the University of Cologne. He has a wide experience in condensed matter systems and problems, such as, for example, spin glasses, quantum impurities and quantum phase transitions, graphene transport, topological insulators, and spin liquids. Some of his close collaborators over the years have been Matthias Vojta, Subir Sachdev, Markus Müller, and Joerg, Schmalian, to name a few. And today he's going to tell us about his work on hydrodynamic electrons in Dirac-type systems, the role of particle-Hall pairs. So please, Lars, the floor is yours.
Thank you, Elsa. Thanks for the nice introduction, and also thanks for the invitation and the opportunity to speak. So I hope that at some point we can do this live, but so now we have the back and forth virtually, so let's hope at some point we can do this live again. So yeah, title of my talk is Hydrodynamic Electrons in Dirac-type systems, and I want to particularly discuss the role of particle-Hall pairs, but this will only be like a relatively short part in the end of the talk. Like I prepared this talk in a, yeah, let's say in a quite pedagogical manner, at least I think. So so I hope I don't bore the specialists, and if I drop you at a very early stage, yeah, just ask questions right as they come up. Okay, so now hydrodynamics. So hydrodynamics is a very old discipline. It has something to do with the motion of fluids. That's essentially what it means. And one of the key concepts in hydrodynamics is the viscosity. And one of the giveaways of a high viscosity in a liquid, for instance, is that it flows slower than a liquid with the lower viscosity. So here, for instance, you have water and honey, and everybody knows they flow at very different speeds. And this is now, I can now make a suggestion which hopefully belongs to the past. So this is a suggestion for, say, lockdown Corona times. If you run out of Netflix, there's actually a really nice thing you can do. There is an experiment in Australia. There's actually a number of them, but this is the most famous one. As far as I know, it's also the oldest one. And it's called the pitch drop experiment. And it was set up in 1927. And so what's going on there is tar has been placed by Thomas Purnell in a funnel. And tar is an extremely high viscosity liquid. So it's actually almost as highly viscous as glass. And yeah, and then they let drops fall down into this cup. And at the moment, as we're speaking, so they started in 1927. It's 10 drops have fallen, and so roughly every decade you get a drop, And estimates are that the next drop could actually be falling anytime soon. So if you want to check this out, this is the live stream. Okay. Now, like hydrodynamics, so this viscosity, it actually also has a number of interesting consequences. And one of them is hinted at in this picture. So what you see here is, you can just think of this as a tube. And one property that viscous liquids have as they pass through a tube is they have a flow profile, and a flow profile that is not flat. So that distinguishes it from, say, individual particles in principle. Moving through a flow profile is in fact a direct consequence here of viscosity, because particles drag other particles along. So so this is also well known from the theory of hydrodynamics or fluid dynamics. And so this is a bit more detailed. So here what you see is you see different types of fronts at which a liquid moves. And it turns out that, this is a fully developed hydrodynamic velocity profile. So this is one of the signatures of having a fluid flowing through something. Okay. Now, and again, so the origin of this is viscosity. Now, let's get to electronic systems. So obviously, when we talk about electronic transport, we speak of flow of currents, and so it's very natural. It's very natural to ask, okay, do these things flow like actual liquids, like water, like honey, like viscous fluids? And it turns out there's two very different situations that we have to distinguish. There's continuum type systems, like for instance, liquid helium-3, which has been studied already like 70 years ago. And then there's, like, my background is condensed matter. Then there's the more condensed matter type, well, not condensed matter, but say solid state type setting, in which we have underlying lattices, and electrons move in this lattice. And it turns out these situations are actually quite different. They're quite different. Now, the question is, how do lattice electrons flow? Like, do they actually flow like a liquid, or do they not flow like a liquid? So if you want an answer at that question, what you can do is you can just open up a textbook. So there's, you can just take your favorite solid state textbook, and there will be a section on Drude transport theory in it. And Drude transport theory is very old. It's more than 100 years. And the underlying assumption in Drude transport theory is, in fact, independent electrons moving through a background of, say, impurities, and then eventually diffusing through the lattice. And so this has nothing in common with standard with the flow of a liquid, because as I said, in a viscosity, so when you have a viscosity, what you have is actually you have layers that are connected to each other via friction and that drag each other along. And here we're talking about a picture of independent electrons. Okay. So so then the question is, so somehow it looks like in order to observe this very fluid type of flow, we need something that glues the particles together. So independent particles don't seem to be the right place to look. And it turns out interactions, like every electronic system has interactions. And it's these interactions that drag each other, or drag the different layers that you see here along. Okay. There's another thing I wanted to mention, because I come back to that later. Like the basis of the theory of hydrodynamics. So like if you talk about the theory of hydrodynamics, you're talking about Navier-Stokes equations, and like when you derive these Navier-Stokes equations, there's a number of assumptions going into them, and the most important ones are that you have conserved quantities. So you have conserved quantities, and the other one is you have local thermal equilibrium. And the conserved quantities that are usually considered are mass or charge, momentum, and energy. So those are the most important ones. Can be others, but those are the most important ones. Okay, now let's get back to this Drude transport theory. So when we talk about transport, like one thing that always comes up is Ohm's law. And Ohm's law, if you formulate it on the level of densities, for instance, means there is a current density J, and it is connected to an applied electric field via the conductivity sigma. Okay. And then based on this Drude theory, or if you want to make it a bit more sophisticated, you can use the Boltzmann equation, which is something I will come back to later. And based on that, eventually all the effects of collisions that electrons undergo and that eventually lead to a finite resistance or a finite conductivity, they are all subsumed in this one quantity, tau, which is the scattering time. So the mean free time. So essentially, the time a particle can travel between scattering events. Okay. Now, there's many effects that can enter this tau, and especially in a lattice. So in a lattice, this is the setup we're looking at. In a lattice, so very obviously we have the lattice, and this lattice comes with a number of scattering of ways of providing scattering. So the red ones here are supposed to be the lattice, and the blue ones are the electrons. Don't get confused later. Red will be the holes. But okay. There's, for instance, there's disorder. So you can have disorder in a lattice. Could be atoms missing. Could be wrong atoms in the places. I mean, many different types of disorder are thinkable. But the one thing they have in common is that if you look at, remember I told you, hydrodynamics is about conserved quantities. So if you look at conserved quantities, well, in scattering events, charge is usually conserved because you have an electron, it hits something and it goes out. So charge is fine. If we consider inelastic scattering, then energy is also fine, which is, I mean, the standard model for modeling impurities, but momentum is not conserved because, electron hits something and then it goes out. It has the same energy after hitting it, but it goes in some randomized direction. Okay, so momentum is not conserved, which is the same as saying translational symmetry is broken. It's equivalent statement here. Now, there's another player here. It's called phonons. So phonons are lattice vibrations. And electrons, they can in fact scatter from phonons. And what typically happens in solid state systems is that these phonons, they can very easily lose energy and momentum that you give to them. And they lose it within their own subsystem. So there's nonlinear couplings between phonons. There's Umklapp scattering in the lattice. So if an electron hits a phonon, the phonon will somehow get rid of this momentum and energy it gets. And that means that for the electronic system itself, momentum and energy are not conserved because they hit the phonons and the phonons just run away with the momentum and the energy. Like if you want to say this more formally, if you consider a coupled system of electrons and phonons, and you ask for the transport properties, in principle, what you want to do is you want to solve a system of coupled Boltzmann equations. And in this system of coupled Boltzmann equations, you have the electrons and you have the phonons, and they scatter from each other. Okay. Now, what I just described amounts to simply saying I solve, quote unquote, the phononic Boltzmann equation by just saying the phonons are in equilibrium because they equilibrate super fast compared to the electronic timescales. And yeah, in that limit, for the electrons, effectively momentum and energy conservation are not given. Charge is still fine because it's electron in, electron out. Okay, now, and then there's Coulomb interactions. The Coulomb interaction is, it actually looks, if you, Coulomb interaction means you have, for instance, two electrons, and they scatter from each other, and you have, again, two electrons coming out. So very, very simply, it's obvious to see we're conserving charge in such a process. On top of that, the momentum of the combined two electrons going into the scattering event is the same of the two coming out of the scattering event. It's just because there's momentum conservation, or like you can put it differently. Coulomb interaction does not break translational symmetry. And the same is true for energy. So if you consider a problem of that type, in fact, we have a check at all these quantities. So all these quantities are conserved. In fact, this looks quite promising for hydrodynamics because I told you hydrodynamics requires conservation of these quantities. Okay, now let's get back to Trude. So it's relatively obvious that in a solid state setting, we will never have a perfect conservation of all of these quantities. It's simply because there will always be imperfections and there will always be phonons. So there's no way around it. They're just there. Now, however, the three processes I discussed, turns out all of them will enter this quantity tau. Now, this quantity tau is just it's just a container quantity for all these different processes. So if you want to formalize this again, you have to look at the Boltzmann equation, and then this is pretty obvious. Now it turns out that this 1 over tau, so this is the quantity you get from Boltzmann, 1 over tau. It's not tau, but 1 over tau. It is composed out of three types of processes. As I just said, there's the 1 over tau disorder, there's the 1 over tau phonon, and then there's the 1 over tau electron-electron. This is the simplest level. Of course, in the end, it's much more complicated because you can have processes where you first run into an impurity, then into a phonon, and then you do a Coulomb scattering. But okay, on the simplest level, that's it. Now, okay, I have to remove that bar. So now usually it turns out that for zero temperature, or in the limit of zero temperature, this is also something you find when you open a solid state book. You get to this residual resistance. So you saturate, and the reason for that is that everything is disorder dominated. So meaning disorder is the dominant scale, and phonon and electron and electron, they take a backseat. Now, if you go to higher temperatures, I mean, don't take this room temperature too seriously. So all I wanted to say here is just you can go to high temperatures. And if you go to high temperatures, it turns out that most of the time the phonons are actually the important scale. Okay. Now this begs the question. Can this quantity actually be the dominant scale at some point? And the reason this is an interesting question is because if this scale is the dominant scale, then we have a chance that that we have approximate conservation laws. So, okay, so exactly. So this is the question. So is there a window in which this scale can win? And if this scale wins, then we can hope to see approximate conservation laws to a good degree of approximation. And then we might end up seeing something like hydrodynamic flow of like lattice electrons. Okay, now, first place to look is our standard theory of metals, which are Fermi liquids. So Fermi liquids are essentially, it's stress-free electrons. They're stressed by interactions. They come with the typical scattering time, or 1 over tau EE, which is from Coulomb interaction. And it turns out this quantity is controlled in a parameter, which is T over TF squared. And this is the usual Fermi liquid theory. Okay. Now, it turns out that this is usually a tiny number. And the reason is that Fermi temperature in most fermionic systems that we look at are just ridiculously high. They're 10 to the 4, 10 to the 5 Kelvin. Okay, so Fermi liquids don't seem to be the best place to look for this hydrodynamics. Now, it turns out there is a good place to look for this hydrodynamics. And so it's my task to tell you throughout the rest of this talk why it is graphene. So, I mean, it's not only graphene, but graphene, as in so many cases, has taken a leading role here in this endeavor. Okay, I also want to show you that there have been strong indications of the observation of this hydrodynamic behavior already in graphene. And and these are like 2 of the key experiments. Like I will mention a couple more as we go along, but those are two of the key experiments. One was done like in Israel and with Andre Geim, that's the left one, and the other one is the Harvard group. And essentially what they looked at is the flow profile of a current going, essentially through, a small system. And it turns out that, and these are complicated experiments, and I'm not going to talk about any details of it, but like the upshot was that they could identify this wavefront. And for instance, I mean, this is not a choice here. It's just easier to see. So I go to the right-hand side. So what you see here is you see a number of profiles here, and now you see these nice, almost like inverted parabola looking flow profiles, and you see these boxes. And the difference between these 2 situations is in fact the quality of the sample. So the super ultra clean samples, they show this flow profile, whereas the quite dirty ones, they show this one. Okay, so this is so this is one of the signatures of hydrodynamic flow. However, this is not what I'm going to talk about. So I'm going to talk about something else, which is bulk signatures. So at this point, I'm at the end of my introduction. So if there are questions now, I think this is a great moment to ask. If there are no questions now, there seems to be one.
Yes, sure. Please, yes, it's Akasdeep. Can you unmute yourself and talk?
Yes, thank you very much. Thanks for a very nice introduction. I was wondering if the electron-electron scattering events do not relax momentum, then why do they contribute to the resistivity?
Okay, this is a tricky one. In fact, you're absolutely right. Like as a theorist, and if you're on a lattice and you look at the standard metal, then electron-electron interactions, they can only relax a current, in fact, if you include Umklapp scattering.
I see, okay.
But this is cheating again, because you're using the lattice again. So in a strict sense, you're right. However, I will argue now in the second part of the talk, I will argue that there are systems in which this tau can in fact really be given by electron-electron scattering, and then there's no cheating. Like you don't need Umklapp scattering or anything. there's a different mechanism at play. But okay, it's a good comment. It's a good comment.
All right. Thank you. Thanks.
Yeah. Okay. So what I'm going to talk about is I'm going to talk about thermoelectric bulk signatures. And so the setup is as follows. I will consider a system like a bulk system. So I'm not worried about boundaries or these kind of things. In the things I just showed you, boundaries actually play an important role. So for what I'm going to talk about, boundaries play no role at all. Now, we assume that we can have two reservoirs at different temperatures, and we can have them at different voltages. So that's the usual setup for thermoelectric transport. Furthermore, I want there to be electrons. I want there to be holes, and in the end, I will argue that in principle, we should also consider something else here. And this is essentially, if you read the title of the talk, you can probably already fill in what's in here. Okay, so this is the general setup. And now, what I'm first going to talk about is I'm just crossing out this part. So I'm just concentrating on electrons and holes. And I'm telling you something about the thermoelectric transport properties in such a setup. Okay. Now, as I said, graphene is kind of it's a driving force in this field of hydrodynamic electrons. And I think it is a driving force for many reasons. One of them is certainly that they can make it at super high quality at the moment. They can make it super, super clean. There's another one, which is that the onset temperature for phonons in graphene is relatively high. So this is also important. And the third one is what I'm going to explain now. So, okay. So if I'm just looking at the very, very basic properties of graphene, at least for my purposes here, for my purposes, it's important that in graphene, I have electrons and holes. So I have electrons and holes. They are linearly dispersing. This is actually not that important. The linear dispersion is not super important here. What's important, though, is that there's a particle-hole symmetry between the two, at least if the chemical potential is zero. And what's also important is that I have this chemical potential that I can tune in an experiment. Okay. Now, as I said, in fact, I could do the very same discussion also for bilayer graphene, like at least in a Bernal stacking. It would not matter. It would be the same discussion. I mean, at least on a very general level. Okay. Now, like one thing that probably most of you have heard at some point is that graphene is a semimetal, and obviously this is true. But what I'm going to argue is that this semimetal, in fact, has very, very funny properties when you consider it at elevated temperatures. And elevated I will define what elevated temperatures means. And and then I will just compare it to a metal. Okay. Now, so first of all, in some ways, if you assume that you have a chemical potential in graphene, mu, which is a lot bigger than temperature, then the fact that you have this hole band here is actually not very important. So in fact, you could get away with a one-band model. Also, the fact that you have this linear dispersion is not super important, because if you just consider a system with a parabolic band, say, and the temperature is sufficiently small and to a good degree of approximation, yeah, things are also linear here. So in that sense, for chemical potential, where mu is bigger than T, essentially we're expecting to find something very much like a Fermi liquid. Now, Dirac liquid, on the other hand, it wasn't me who invented that. It's Joerg Schmalian's and Dan Sheehy's words. So the Dirac liquid is something you should think of in the following way. So if you are at the Dirac point, like right at the Dirac point, it turns out, and this is something that had been done, this was introduced in 2007, but before, people often considered zero temperature properties. But what they argued is that it is actually not a very reasonable limit to take if you're right at the Dirac point. Because if you're right at the Dirac point, you have a system with no energy scale whatsoever. This is, in fact, very similar, or not very similar, it's the same if you're in a quantum critical system, if you're in a quantum critical system at the critical point. Okay. Then temperature is the only energy scale. And it's not a very meaningful exercise to take it to zero, because usually when we take T to zero, what we actually do is we take T over TF to zero, because T over TF is a parameter, T is not. Okay. So, right. So if we're at the Dirac point, it's not even a useful statement to say we have high or low temperature, because temperature is just order 1. Unless there's other things around. Okay. Now, but this also means that there has to be a crossover region between the two, because you can imagine having a finite chemical potential, let's say a small chemical potential. And now we can think of two situations, one in which temperature is smaller than the distance to the lower band. Then the lower band should not really matter for many purposes. Or one in which it is bigger than the distance. And then we should really worry about both bands. Okay. So so this is the actual definition given in their paper is a bit more sophisticated, but this is in zeroth order. This is the statement. Fermi liquid for T smaller than mu, and Dirac liquid for T larger than mu. Okay, so when in the spirit of quantum phase transitions, we can then also draw something like a phase diagram, where we have Fermi liquids over here and a Dirac liquid over there. It's just important to note this is not really a phase transition here. There's nothing. It's just a crossover. Okay. Now, as I said, this was introduced in 2007 by Sheehy and Schmalian. Now, I told you about Coulomb interactions, so let me introduce the setup. So the setup now is that we have the Dirac electrons of graphene. So it's the linear dispersion. I've written down the Dirac form, but as I said, the spectrum is linear, but that's the important thing here. And we have a Coulomb interaction, which is also, it's just there because it's there. And it turns out that, importantly, Coulomb interaction does not break translational invariance. Turns out that alpha here is a dimensionless parameter, and in fact, it's like the fine structure constant of QED. So it's dimensionless. Instead of if you look at the QED, you would find a C standing here. Here you find a VF. And that also means that unlike in QED, where alpha is 1 over 137, it is let's say something on the order of 1. Something on the order of 1, it actually depends on the dielectric constant of the environment. Okay, now a word on transport properties. So this connects to the question that was asked before. If you're in a normal metal, then and you apply an electric field, just say you have a normal metal, you're at the chemical potential sits somewhere at some energy. And now you apply an electric field. What will happen is your electrons, they will start to move and you will excite momentum. And so you will excite a total momentum, which goes with current flow. And if there's nothing around, if there's no impurities around, this will just go on. Like there's nothing holds it back. So if you, I mean, it's the same as saying I consider a system, free electrons, no interactions, no disorder, no nothing. And I calculate the conductivity of it, you will find it's infinite. And that's simply because like the moment you excite some momentum, which you do because you apply an electric field, you cannot stop the electrons from just getting faster and faster. Okay. Now, and this is what makes graphene special in that regard. In graphene at the Dirac point. So if you're at the Dirac point, then you have a total charge of your system, which is 0. So the total charge in your system is 0. However, that doesn't mean that the individual charges are 0. Like, I mean, and the reason is again this finite temperature, because we are, as I said, we should always consider finite temperature. If we are at finite temperature, it turns out that like there will be a thermally excited cloud of electrons, but also of holes. And in order to comply with the 0 charge, they will have the same density. So they combine to 0, but they're individually. It turns out that if you apply an electric field to this system now, the electrons, they will react in a quite different manner to the electric field than the holes, because like they have opposite charges. So one will go this way and the other one will go that way. So this clearly has a current flow, because if I go this way with electrons and this way with holes, so this way with holes is the same as saying electrons are going that way. Because, I mean, if you think in terms of current flow. So you have finite current, but you have zero momentum. Like the total momentum stays put at 0. So that has one immediate consequence, which is like we're not, okay, sorry, this was not where I, yeah, okay. So this has one immediate consequence, and this consequence is that we don't have to break translational invariance to relax the current, because we're not exciting current and momentum at the same time. So the best way to think of this now, what leads to a finite resistivity in that system is, think of electrons and holes, and there's a friction force between the two. Like another way to put it, like a more formal way to put it, is there's drag. So they drag each other along, and that eventually can lead to a finite scattering time between the two. Okay. Now, okay, you can do some estimates of that. But okay, I'm not going into the details of this now. So yeah, we expect something of this type, and like what I said in words, like with the frictional force, of course you can make an actual calculation. So there's an actual calculation that you can make, which is behind all these words, and this calculation is based on. I mean, this is just what we did. We did it with Boltzmann. You can also use Kubo formula if you want. But if you use a Boltzmann equation, then you can determine the conductivity at the Dirac point. And the conductivity turns out to be given like in an expansion to lowest order in a Coulomb interaction. It is given by this number, 0.76, but that's just the number which comes from the solution of the Boltzmann equation. E squared over h, that's because two-dimensional conductivity is just something, E squared over h times something. and then 1 over alpha squared, where alpha is the fine structure constant that we just introduced. Okay. Okay, it turns out that 2-3 years back, people managed to make an experiment that measured this bulk transport quantity. And so in fact, this is the important plot here. This is the important plot where they measured the scattering time. And if you convert their result into a conductivity, you find an excellent match for a value of alpha, which is 0.23, which is in agreement with estimates that people made for the type of setup that was looked at, which was sandwich graphene, like this boron nitride sandwiches. Okay. In fact, there's another interesting one, which I only discovered. In fact, I only discovered last week for strange reasons. But the same type of measurement has been done in bilayer graphene. And I mean, I told you that the same story, in fact, applies to bilayer graphene. And so it was in this paper. It's already a bit older than the other one. In the experiment, they measured a sigma which was compatible. Oh, I have to go back. I want to get rid of. Okay, good. So, so they made a measurement of the the conductivity at the charge neutrality point, and they found an expression, or they found a result which was compatible with something between, I mean, they say between 12 and 24 times E squared over H. And in fact, I looked at an old paper that I had with the master's student, and where we made the calculation, and we found, at the time, we found sigma of 27 times E squared over H, which is actually not such a bad agreement, I would say. And yeah, again, this 27 comes from solving a Boltzmann equation. So there's no easy way to understand it. It's just a number which comes out of solving a Boltzmann equation. Okay, now let's look at the transport properties in a bit more generic sense. So now up to now I discussed charge transport, but the title of the talk is thermoelectric transport. So I should also say something about the like electric thermal transport. So this is the full setup now that I consider, and there's this famous tensor expression which relates charge current, heat current to applied electric field and applied thermal gradient. And here we have like the conductivity, and what we usually call the thermal conductivity is in fact not this kappa bar, but it's kappa, which is kappa bar minus T times alpha squared. So alpha here is not the fine structure constant. Sorry for that. This is not the fine structure constant. T times alpha squared divided by sigma, where like what's underlying this kappa is that you're driving a heat current under the condition of no electrical current flow. So you're imposing that, and then this is the resulting response coefficient. Okay. Now, one interesting point here is that contrary to what I told you about the electrical conductivity, the heat conductivity at the Dirac point is actually not finite. And the reason is that the electrons and holes, they will react the same way to a temperature gradient, which means a temperature gradient will excite momentum, which also means that if I'm not adding any type of disorder, this kappa will be infinite. So, I mean, when I say adding disorder, I'm speaking as a theorist here. Like, As an experimentalist, disorder will be there. So there's nothing you have to add. But as a theorist, for me, I have to add disorder now to make everything finite and well-defined. Okay, now there's one interesting quantity in the study of thermoelectric transports, which people often look at, which is the Wiedemann-Franz ratio. The Wiedemann-Franz ratio is the ratio of kappa over T times sigma. So thermal conductivity divided by T times the electrical conductivity. And it turns out in like many metals that you find, so this is a surprisingly universal quantity. It's a surprisingly universal quantity. In fact, many metals, and this was actually already established in the 1850s. So this is really old results here. Like, so they just measured a whole set of metals, and they found that this ratio always went to the same value, essentially. Okay, and so you get to this like universal ratio, which only involves natural constants. Okay, now so is there a simple way to understand why this usually happens in Fermi liquids? Well, I essentially gave away the reason already in the introduction. So usually what happens is like at very low temperatures, transport properties in standard metals, they're disorder dominated. And this applies both to thermal and electrical transport. So they are limited by the same type of scattering event. Like the same type of scattering event limits both. Okay. Now, like if you think of it, it goes this way. So there's a kappa, which is a function of T, and there's a T times sigma naught, which is a function of T. Now, this kappa will have a 0-point conductivity, which is disorder limited, and then there's inelastic scattering on top of it. Elastic scattering on top of it. And the same is true here. And they are both controlled in this parameter, which usually is very small. So this is a very small parameter, and those two quantities here, they are limited by the same type of scattering events, which means the tau cancels, and thus all the microscopic information is gone. And all that remains is in fact just this. Okay. So, right, so this is usually set by impurities. This is super small. But okay, in graphene, first of all, if we're at the Dirac point, TF is 0. So this is not small. And also we just saw, there's actually, it's even worse than that. Like this guy here is infinite, whereas this one is finite. So at the Dirac point, formally, if you disregard this order in graphene, but again, this also applies, for instance, to bilayer graphene, or to any system which has this particle hole symmetry, for that matter, this thing will diverge. Okay, so obviously one needs to include the effects of disorder now to make a controlled calculation, also something that connects an experiment. Okay. Now, and this is where I come to the and okay, this has been done in various places, but I want to come to something new now, which is what we're working on at the moment. So this is work in progress, and what I'm trying to convince you of is the following. So what we are looking at is a Hamiltonian, like it's this interacting Hamiltonian. And now one thing that enters, or the thing that enters our calculations is the heat current operator. And usually when people write down the heat current operator, they write it down in this way. So, or maybe, okay, this maybe not the most common way to write it down. Often you will find something like quasi-particle energy, distribution function, and the velocity. but this is an equivalent statement. And okay, and that's it. But it turns out that this is actually not entirely true. And the reason is this term here, because this term, in fact, it can carry, if you just look, if you just try to derive the heat current operator, in fact, you should take this guy along. But now you have a problem because this thing is non-local. So let's say you want to derive an expression for the heat current operator using Noether theorem. Then like you're a bit in trouble here because of the non-local character. Okay, so we were wondering whether how we could incorporate that. Now, like the way to do that is, in fact, we start with the interacting term, which is non-local, and we make it local. Like formally, the way to do that is by a construction which is called Hubbard-Stratonovich construction. So essentially, you're replacing one of these. It's a bit like mean field, but you keep mean field as a dynamical field. So you're replacing one of these densities here with an effective bosonic field, and the price you pay is, in fact, that now you have a coupled field theory of electrons, bosons, and essentially they're coupling. So this is the coupling between the two. This is electrons and this is bosons. And now you can use Noether theorem. And what you find is that there's an additional contribution now. And what we were trying to understand is how big is this contribution really? Like, is this something which is completely negligible, or is it something that can be big? So the usual belief is that in a Fermi liquid, this is suppressed. This is suppressed. And this is actually also something that we don't fully understand at the moment yet. But so to tackle this, just to give you a flavor. So I was using a lot of cartoons so far, but also to give you a flavor of what we're really doing is, like, we're doing these coupled field theories, and we start from a full, like, many-body Keldysh approach. And after like a number of steps, we get to a more conventional looking Boltzmann equation. And this Boltzmann equation now, as I said, it's the electrons and the holes, and they're coupled to a bosonic degree of freedom. Turns out this bosonic degree of freedom is particle O pairs or plasmons. So if you follow this logic, and okay, and now we're studying the combined system of equations. So this requires a fair bit of numerics. So this is actually technically quite annoying. So this is annoyingly complicated, let's say. So I'm sparing you all of these details. However, there's one thing which is important to say here, which is that plasmons in 2D, they're quite peculiar. So they're different from 3D. In 3D plasmons, they are known to have and this is knowledge which goes way back, Pines, Bohm, Noether. They have a gap which is on the order of the Fermi energy. So it's huge. So for usually for practical purposes, you can forget about plasmons when you talk about thermoelectric transport properties, because they're just the gap is so huge, so they're not even excited. Turns out in 2D it's very different. They're gapless, and they come with the square root dispersion. On top of that, what I mean here with irrespective of dispersion is, I mean, this is true for graphene, but this is also true for a bilayer. This is actually even true for just a 2D, like a parabolic band. So it doesn't matter. They're remarkably stable. So they have very, very few chances to decay. Usually they need phonons to do that. Okay. And then we just look at this combined set of equations, and we calculate, for instance, the electrical conductivity, which is the curve that you see here. So this is the electrical conductivity of graphene around the Dirac point. And we can do the same for the thermal conductivity. And this is where we were actually surprised. So initially, like my expectation was that we should see an enhancement at the Dirac point. When I just told you Dirac point is something where we have like formally an infinite thermal conductivity of this electronic model. So what's happened here in this plot is we've actually used some disorder. So we've added some disorder into the mix to make sure that the kappa does not explode. Okay. Now we add this plasmon contribution on top, and it turns out it doesn't do a lot around the Dirac point, but it has a contribution that grows as we go away. So it actually contrary to what we first thought, it looks like it's growing towards the Fermi liquid. To my knowledge, this has not been discussed anywhere. I mean, if somebody knows, I'm interested to hear, but I really couldn't find anything there. And that also means that if we look at the Lorentz ratio, so keep in mind, L is 1. So 1 here, this is the Wiedemann-Franz line. So I haven't drawn it in. So if we just look only at electronic contributions, so I'm neglecting plasmons for the second, then we find that the Wiedemann-Franz law actually, as you go into the what we call Fermi liquid regime, it saturates around 1. So it goes towards a value of 1, which is what you would expect and what you would hope for. However, if you include the plasmon contribution, then you will find that not only is there a stark deviation at the Dirac point, so that deviation I explained, because you have like this infinite versus finite, and then you have a disorder, and that acts differently on the thermal and on the electrical transport. So that one you would expect, but this one is actually something that we didn't expect. Okay, so this is something that you can find on the archive, but we're at the moment we're also busy looking in various other quantities, like how does this work for bilayer graphene? How does this actually work for bilayer graphene? Can we derive effective hydrodynamic equations? And many more questions. Okay. So I think with that, I'm at the end of my talk. I hope I got the timing right, and I'm happy to take questions.
Thank you very much, Lars, for this wonderful talk, and thank you for making the effort of giving such a good introduction. Yeah. So, well, I see already some questions. Alberto, please unmute yourself and go ahead. Thank you.
Okay, thank you. Thank you very much, Lars, for this nice talk about hydro. I have a simple question. Maybe it's a question of ignorance, or you have some technical details behind it. As far as I know, plasmons at the Dirac points are not well defined, right?
At finite temperature, they are.
Okay.
It's again one of these things. If you look at the 0 temperature result, then they are not there. But like at finite temperature, they exist. However, like their weight, if you want, is small. It's just temperature itself, and essentially you can. Okay, no, I was drawing on it. Essentially, you can see here like the enhancement is not very big. So in fact, the prefactor of the plasmons, like okay, in the dispersions, you have omega square root k. And there's a prefactor which comes with it. And this prefactor contains something like the maximum of mu and t.
But also they are overdamped, right? So the question is how overdamping enters in the...
No, they're not overdamped.
No, I mean, so they are not overdamped at finite t, right? But still there is some overdamping. They are damping in the... So they are, there is some damping depending on t, I guess. So the question is, in your calculation, you took into account this kind of because there are papers by people saying that when you compute the plasmons, And if you resort on these RPA calculations, you get these overdamped plasmons. But you go and take into account ladder diagrams to consider the plasmons at the Dirac point. You enhance or you reduce the damping, and then there is an extra peak in the plasmon spectrum.
Do you happen to know which paper this is?
Yeah, it's a PRL by I forgot the guy. It's a PRL. I can send you a reference later.
That would be good. So okay, I mean, we consider them indeed on the RPA level, and there they are very stable.
Mischenko is the author. Sorry.
Sorry.
It's Mischenko.
Mischenko. Okay. Yeah. Okay. I'll have to check it. But yeah, indeed. I mean, on the RPA level, they're very stable. So if there's something we're overlooking, okay, I have nothing clever to say about that.
Okay, don't worry. I can send you the paper just to see if it's important or not.
Yeah.
Thank you very much for your answer.
So there is another question by, I think it's Jaime Ferrer.
Oh, yes, indeed. Thank you. Can you hear me?
Yes, I can.
Okay, so thank you for your nice talk. I just wanted to ask whether you have some estimates for the thermopower. What would be the contribution for the thermopower?
Actually, we haven't looked at this at all yet. So we really haven't. I mean, I should probably be like it should be easy to figure out from what we have, but okay, I simply haven't done it.
Okay.
But it should be in the equations that we're solving.
Yeah, it was just a question of whether it could be enhanced or not.
Okay, that's a good. Okay, I don't know. I mean, we haven't looked at it.
Okay, thank you.
Yeah.
Thank you. I have a very, I don't know, naive question. So you say that you need an spectrum that is particle-Hall symmetric. And I wonder, can you have a gap between the conduction and valence bands, and all this would still work?
Yes. The only thing you need is, in fact, or you probably want the temperature to be comparable or bigger than the gap.
Yeah, I can imagine. Mm-hmm.
But other than that, it really doesn't matter. It really doesn't matter.
Okay, so it could be extended to other two-dimensional crystals that are semiconductor.
Yeah, exactly. Yeah.
Mm-hmm. Okay, is there any other question out there? If not, let us thank the speaker again. We are already past the hour, so thank you very much, Lars, and thank you everybody for being there.